Now we're going to introduce the topic of thermochemistry or thermodynamics. And this is the study of energy and the transformations energy may undergo. There are two trends in nature. We're going to look at energy transfer. If you go on to 1062, you'll also look at the trend in nature to go from a more ordered system to a more disordered system. So we're going to focus on energy transfer. And this is a downhill process. So energy is always transferred from a region of high energy to a region of low energy. So what is energy? By definition, the capacity to do work and/or the capacity to transfer heat. There are two general forms of energy we're going to look at with respect to what they're related to, and those are kinetic energy and potential energy. So let's go back to the capacity to transfer heat. So that means we're moving heat from one object to another. And it's always going to be in the direction or flow of high heat to a lower heat region until an equilibrium has been achieved. So think about it this way. When an ice cube melts in your glass of tea or soda or whatever you're drinking, heat is being transferred from the warm liquid or warmer liquid in that glass to the ice. So the liquid is warmer than the ice, so the heat transfers to the ice, and as a result, the ice begins to melt and the surroundings cool down. So that's how ice cools your glass of soda or iced tea. And again, heat always transfers from higher temperatures to lower temperatures until a thermal equilibrium is achieved. So the two forms of energy, kinetic energy, is energy associated with motion or movement. Potential energy is energy associated with position or composition. And we can think of that in two ways. Position, let's talk about, let's talk about kinetic first. Kind of a real world example. Most of you have probably played pool at some point or even watched someone play pool, where you have a cue ball and then you have maybe the 8-ball here or some other ball. You hit that cue ball with the pool stick and it immediately thrusts off and hits that cube or the 8-ball. If you hit this ball hard enough, it may even come to a dead stop. But what happens is, if that happens, all its energy has been transferred to that 8-ball and it moves. Potential energy can be associated with position or composition. Let's talk about a roller coaster. Most of you have probably ridden one of those. If you're in the roller coaster car, right on the verge of this downhill portion of the track, you have very high potential energy. So you have energy that's associated with the position. And once that car teeters over the edge, potential energy decreases and kinetic energy increases due to that motion or movement of that roller coaster car. Composition, on the other hand, when it's applied to chemistry, is the potential energy stored in chemical bonds. So let's just look at HCl, for example. This will be for any covalent molecule that has a bond here. Can also apply to an ionic bond, and we'll see evidence of that in our calorimetry experiments. But there is potential energy or chemical energy stored in that bond. Okay, so that's potential energy because of its composition. These are just some other types of energy. We're going to focus on thermal energy, which is going to be associated with motion of atoms and molecules. But we survive on this earth because of radiant energy that comes from the sun. This is our primary energy source. If we didn't have that, plants wouldn't be growing, we wouldn't have sources of food. So we're kind of in a dependent or adaptive dependent cycle where we rely on the energy from the sun to provide and generate processes here on Earth. Chemical energy, again, is that potential energy stored in the bonds of chemical substances. And of course, nuclear energy is the energy stored within the nucleus of an atom. And it's the protons and the neutrons that are responsible for that nuclear energy. So, heat is defined as the transfer of thermal energy between two bodies at different temperatures. Temperature is a measure of thermal energy. So in the lab, when we measure the temperature change in a reaction, we are measuring the transfer of thermal energy. But that doesn't mean temperature equals thermal energy. And one more thing to think about. We have we have a cup of coffee here. So we have a container, small container, contains hot coffee at 90 degrees Celsius. And we have this big bathtub with the shower running and a temperature of 40 degrees Celsius. Now, both of these containers have the capability of transferring heat to the surroundings. You've touched or maybe held a cup of coffee or tea or hot cocoa to warm your hands, perhaps, in the winter. But this container, the bathtub, is also capable of transferring heat. So the question I would ask of you is, which of these scenarios transfers the most heat or has the greatest thermal energy? The cup of coffee or the bathtub? Keeping in mind that thermal energy is the heat transfer between two bodies at different temperatures. And these aren't transferring to bodies, but they're transferring to the air around or their surroundings. And it might surprise you, or it might not, but the container, the bathtub, has greater thermal energy because it has a larger surface area. So it is transferring more heat to the surroundings than that cup of coffee or tea. Some more terminology and definitions. So when we look at when we study heat transfer, we have to define a system. So we are choosing a portion of our universe for study, and it's not a very big portion. So this is the system, and the system is surrounded by the rest of the universe, or whatever's outside of the system we're studying. And there is a boundary, and the boundary separates the system from the surroundings. And in our cases, we will be insulating the system from the surroundings in order to study heat transfer. So let's look at the different types of systems. Before we move on, but let's also look at the term thermochemistry. This is the study of heat change in chemical reactions. Okay? And the system is the specific part, in this case the chemical reaction, that is the interest in our study. And there are three ways to do this, or three types of systems that can be utilized, and we're going to compare them. In the first system, this is an open system, and so here we have a container. It has something hot in it, let's say. The characteristics of this container are it's open to the atmosphere and there's no insulation, so heat can be transferred into the system or out of the system. And mass in the form of water vapor can be transferred out or in. So in an open system, both mass and energy can be transferred. Now in the second scenario, we've capped this bottle. So now we've stopped the transfer of mass into and out of the system, but we still can transfer heat into and out of the system. So this is a closed system where only energy can be transferred. And the final system is the isolated system, where we have now insulated our container, which prevents heat transfer into or out of that system. Nothing can move in or out of that bottle. So that's the isolated system. Another example you could think of, hot soup in a thermos. It does not transfer heat or matter with its surroundings, at least until you open the container. And then it's no longer an isolated system. So, three types. We can also classify chemical reactions, or the transfer of heat, depending upon whether it gives off heat or absorbs it. An exothermic process releases heat or gives off heat, transfers thermal energy from the system to the surroundings. So chemical reactions and physical changes release or absorb heat energy. Here's an example. This is written as a chemical equation, but this is the formation of water, where we have gaseous hydrogen, gaseous oxygen reacting to form liquid water, and when that happens, energy is released. So it's shown as a product, and this is an exothermic process. Here's the phase change, where gaseous water is condensed to liquid water. So phase changes transfer or have thermal energy transfers. And this too is an exothermic process, or releases heat to the atmosphere or surroundings. Endothermic processes are the opposite. They absorb heat from the surroundings. So energy, or thermal energy, is a reactant in this process. Here we have mercury oxide decomposing to mercury and molecular oxygen. That requires energy absorbed from the surroundings. So it's an endothermic process. And here's another phase change where solid water is converted to liquid water. That requires energy in order to melt that water. So it is an endothermic process. So here's a graphical representation of exothermic and endothermic reactions. And if you look at what this reaction is, we can see that it is reverse, one's the opposite of the other. So, and graphically, we can look at this in terms of energy. So this is an energy diagram. Energy increasing, this is the course of the reaction. In an exothermic reaction, the reactants have higher energy than the products. And this decrease in energy here is given off as heat. So this is the heat associated with this chemical reaction. And this is the reaction of the combustion. Oh, this arrow should be up here. Moved from its proper location. Combustion of glucose to form CO2 and water, plus energy. So this is a process that occurs in our bodies. We metabolize glucose to obtain energy from that molecule. On the other side of the spectrum, the production of glucose and O2 requires solar energy. So plants use solar energy, CO2 from the atmosphere and water to produce glucose and oxygen. So that's our interdependence shown again right here based on that solar energy. This energy diagram, the reactants have lower energy than the products. And the difference in that energy is the energy that is absorbed in order for that reaction to take place. We're going to end here, but start our next discussion introducing how we look at and analyze heat flow in chemical systems.